Good evening, esteemed colleague and distinguished guests. My name is Minu Jafarlu, and I'm thrilled to share my our research on improving a fuzzy logic-based map matching method with trajectory state point detection. I want to thank your conference for providing the opportunity for me and for my coworkers to present our work. And I also want to thank my advisors in this research, Dr. Abadati and Dr. Naderi. This research was conducted in Kharazmi and Iran University of Science and Technology. Let's start. This is the outline of our topic. We're going to talk about the introduction, then we're going to talk a little bit on a literature review of this research, and then we're going to talk about preliminary investigations to gain a deeper understanding of the problem at hand and explore potential solutions. And later, we're going to talk about the proposed method and results. Then we're going to finish this topic with conclusion and references. A wide range of management plans and intelligent transportation system requires fast and accurate location information, including urban traffic management, navigation system, accident management, and emergency responses. The most common locator devices in urban area is the GPS, which stands for the Global Positioning System. GPS trajectory data must be matched to the road network using map matching algorithm to analyze and use vehicle trajectory in the spatial road network. In fact, map matching algorithm assemble the raw data into selected road segments in order to track vehicle movement. You can see the figure on the left regarding this. But GPS devices may malfunction in some cases, particularly in dense urban environment, while with tall buildings where it can be challenging for satellites to locate moving objects. As a result, GPS location data in such an environment can be inaccurate and report the position of moving object with some error. Map matching uses these noisy inputs and may mismatch the point to the wrong road. To solve this problem, we remove unnecessary noisy inputs from the map matching process, achieving more accurate results faster. Our goal is to improve the efficiency and reduce the processing time of this algorithm. In fact, abnormalities and errors in GPS trajectory may cause inaccurate results in map matching process. One of the most critical problems with raw GPS trajectory dataset is the stay point problem. You can see the figure of the stay point problem in the right figure. This problem imports many GPS points into the dataset that are unflavorable in the map matching process and also misleading. Besides, processing all of these points in the map matching process increases the algorithm processing time. Noted state points needs to be deleted from the data set for two main reasons. First, the processing time is crucial in analyzing, evaluating, and comparing a method with other methods. Secondly, these points may lead to a disturbance in the map matching process. Map matching algorithm mostly uses the direction of the vehicle and the distances as input. Stay point regions have a drastic effect on these two parameters. If these parameters are inaccurate, the map matching algorithm may match the points to unrealistic route. This mismatching could even change the point's direction up to 180 degrees and create a matching problem. Map matching algorithms are mainly used in navigation, mapping, tracking. In some cases, navigation algorithm uses online data. However, tracking and mapping methods usually work with offline data. Map matching algorithms mainly are split to four leading groups: geometrical map matching, topological map matching, probabilistic map matching, and advanced map matching algorithms. Advanced map matching algorithms predominantly use fuzzy logic, hidden Markov model, or Kalman filter algorithms or such. These algorithms estimate the GPS point location more accurately. However, attaining these exactness costs a high processing duration. Viewing this point, we choose to work with fuzzy logic-based map matching due to its precision in matching high-frequency sampling GPS points. The other classification for map matching can be based on their sampling rate, which could be high or low. These are our research questions that how can the accuracy and efficiency of a fuzzy logic-based map matching algorithm be improved in urban environments with inaccurate GPS data? Can we eliminate the state points in raw GPS trajectory and enhance the performance of map matching algorithm? It's worth mentioning that our data is processing offline, and the roadmap that we consider is a complete map. And our research hypothesis is that by applying DBS scan clustering method, can we identify and eliminate the necessary data points? The processing time of the map matching algorithm can be reduced while maintaining accurate link identification and data reduction. What is the definition of map matching? Map matching process needs a digital road network and GPS trajectory as input. The digital road network is a simulation of the road system shown with arcs and links, like a real road network. This simulation consists of many resembled roads, junctions, and dead ends. The process of mapping GPS points on the link of the digital road network is called map matching. The two fixed point and matched point concepts are going to be used in this research, so I want to clarify what they mean. Fixed points indicate on the point that map matching process is not applied to them. However, when we're talking about the match points, these are the ones that map matching process was performed on them. For evaluation methods, there are two standard criteria for evaluating the map matching methods. The first one is the processing time and processing time of the method, and the second is number of the correct matches and wrong matches roads. The fuzzy logic-based map matching process has two steps: finding the correct link the vehicle is traveling on, and tracking the vehicle along with the link. Finding an initial correct link and finding a correct link when the vehicle crosses an intersection. Figure on the left illustrates this process, and the algorithm shows the pseudocode of this process. Selecting the initial link to assign the initial position is known as the initial map matching process, IMP. The IMP uses two variables as an input: fixed point perpendicular distance to the link, and the directional difference between vehicle's motion and the link direction, known as heading error. And we're going to create fuzzy logic based on these values for IMP. After IMP, we need to subsequent map matching process. The subsequent map matching process, or SMP, is a process to match the fixed point in the sequence of IMP. Two models of SMP are proposed. The first one is SMP1, the second one is SMP2. The SMP1 is along with the link, and the SMP2 is at the intersections. SMP1 aims to map match the succeeding point with the link identified by the IMP or SMP2. SMP2 detects a new link for the first point among voluntary links when the vehicle crosses an intersection. After SMP2 detects a new link, SMP1 resumes the matching fixed point following the new link. But how SMP1 works? Subsequent map matching process along with the link determines whether a subsequent fixed point corresponded to their previously selected link, like the figure. A is the previous map matched point, and B is our current fixed point. The task of SMP is to select the correct link for the following fixed point B. Expression D refers to the distance between the last matched point on the map and the intersection, and D2 refers to the distance traveled by the vehicle during the last period. The distance between these two distances, delta D, can be used to observe whether the vehicle is crossing the intersection or not. For example, if delta T is negative, it's more likely that the vehicle has already crossed the intersection. Both alpha and beta defines the position of the fixed point B in connection with link A. If both of these angles are less than 90 degrees, it's more likely that the vehicle did not cross the intersection. The angle theta and theta prime are the vehicle's direction indicator at B and A, respectively. The absolute value difference between these two angles provide B's heading increase, in the last period. Therefore, the FIS fuzzy variable are these five: vehicle speed, heading increase, distance traveled by the vehicle during the last period, and alpha, and finally beta. This FIS output is a probability of matching the new fixed point with the same link as the former fixed point. Subsequent map matching process in the intersection, which is SMP2, starts when the vehicle passes the intersection. Like IMP, the functions inputs are fixed points, perpendicular distance, and heading error. Besides, link connection and distance error input variables are used in FIS. The device is moving on a link 1, so the last map match point is on link number 1. SMP2 selects a new link for point B. Volunteer links for this point are link 2, 3, and 4. Since the previous point's position is on link 1, the link connection is an essential criteria for identifying the correct link. The expression D refers to the distance traveled by the vehicle during the last period. If the device is on link 2, 3, and 4, then D2, D3, D4 represent the shortest path traveled by the vehicle. The distance error in the difference between D and D2, or D3 or D4, the link that provides the least distance error is a strong candidate for the correct link. So now that we know how fuzzy logic map matching works, we need to identify state point regions. Raw trajectory datasets have various primary noises. The most important one is these datasets in the state point problem. In this case, the navigation sensor misses the satellite and reports unrealistic location of an immobile moving object. It seems that the moving object is moving in a strange and confused pattern instead of staying in the fixed coordinates. Figure on top illustrates the state point regions. This abnormality in the data set can mislead a map matching algorithm and prevent it from reaching an accurate result. The mismatching problem is evident in this figure. Even if it doesn't miss the satellite, it will send the previous location signal to the satellite and increase the dataset size. In the end, it will damage the accuracy and processing time of the map matching algorithm. Two parameters are used to identify stationary point time and distance threshold. If the time is more than a threshold and distance is less than some threshold, we realize that we are dealing with state point region. DBSCAN is a popular clustering algorithm that can be effectively used for trajectory clustering due to its ability to handle data with a variety of densities, irregular shape data, noise handling, parameter flexibility, trajectory segmentation, and efficiency. And this algorithm is introduced in 1996, and it determines cluster and noises in the spatial datasets. The two parameters were used in this method to shape a dense area. The first one is epsilon neighbor. The epsilon refers to the parameter that determines the radius or distance within which neighboring points are considered as a part of the same cluster. It stands for epsilon and represents the maximum distance between 2 points for them to be considered neighbors. And secondly, the minimum number of points for each point. The neighboring points are defined as points that exist within a radius of epsilon. It's essential to plot the dataset's nearest neighbor to determine the optimal value for the epsilon parameter in DBSCAN clustering algorithm. Determining minimum point for the DBSCAN algorithm is often extracted from the problem definition itself. The plot, which you can see in the figure, computes the nearest neighbor for each point in the dataset and arrange them in ascending order. The plot shows us a variety of density levels in the dataset. A sharp spot in the plot, which named elbow-shaped, represents good values for the epsilon parameter. However, if the dataset has a great variety of densities, the curve would have multiple sharp spots. In other words, the elbow method is used to find the optimal amount of epsilon. The elbow of the diagram corresponds to the threshold for sudden changes in the diagram. In the figure, it is presented a plot with 3 level densities. Each sharp spot stands for a different density level. As seen in the diagram, there are 3 sharp changes in the curve. These sharp changes mean there are 3 suitable values for epsilon parameters. The map matching inputs are GPS trajectory and topological geometrical information. We use these 2 inputs to determine the road on which the vehicle passes. The GPS trajectory that we are using is collected from the movement of the vehicle on the road of Seattle with 7,351 GPS records. The dataset includes latitude and longitude with a timestamp. The data are recorded in an 80-kilometer trip with a data transmission frequency of 1 Hz. This data is used to test map matching algorithm, evaluating each method's efficiency and compare the techniques within each other. Seattle GPS trajectory dataset and the corresponding digital road network is shown in the figure on the right. And also the Grand Truth dataset is designed for testing the map matching algorithm. On the image on the left, you can see the state point problem within our real data set. And while I was talking about the inputs of the map matching algorithm, let's talk about the digital road network input as well. This is a computer simulation graph of the city's road network. This information is used to determine the direction and curve of the road. Our input data consists of edge ID, line string, and node ID. Line string is a multiple connected lines represented the road. Each edge ID represents a road section. Each road is determined by the segment of the line called a link. Fuzzy logic map matching algorithm will identify the corresponding link for each point. Then output area is a string of associating links. The Grand Truth data that I mentioned also contains a true path as a edge ID that a vehicle encountered during the test trip. The valid route includes 399 road edges. So why we pick DBSCAN for clustering? Other approaches such as specified time span, the maximum number of points per second, distance threshold, and standard clustering methods might be used to cluster and reduce state points. Although these approaches may help to get closer to the result, none of them have satisfactory outcomes. When points are close to each other, for example, when the vehicle is in the traffic jam, considering a threshold to delete data points might lead to eliminating variable data necessary for the map matching process. On the other hand, other clustering algorithms do not work as well as dbScan for trajectory clustering. dbScan produces the most accurate results among existing methods. As a matter of fact, dbScan defines cluster based on the local density of the data element in a big spatial dataset. Moreover, it's robust to outliers and do not require the number of cluster predefined. Choosing dbScan for clustering data is paramount since points in fewer dense areas separates the cluster in dbScan. In other words, we can say that lower density zones splits the regions. These components make dbScan less resistant to the noise and cluster shapeless trajectories more efficiently. dbScan clustering solves our problem by clustering the unnecessary data and reduce the size and time. The architecture of the proposed method is depicted in this picture. We use our GPS trajectory inputs, and then we cluster them. We eliminate the redundant data, and then after that, we feed it to our fuzzy logic-based map matching algorithm. In the results section, we're going to discuss first, we're going to talk about the result of dbScan clustering on the dataset, and later we're going to discuss the result of a fuzzy logic-based map matching algorithm. As mentioned earlier, there are two main criteria for evaluating map matching approaches. The first is the processing time of the scheme, and the second is counting the number of the correct and incorrect broad link matches. In addition, the volume efficiency and the speed efficiency for each point are calculated for as an evaluation and more comparison. To select the epsilon, we look at the diagram's behavior for the point of its nearest neighbor. The value of 3 for the minimum number of points based on the data sets data density is selected. So we calculate the nearest 3 neighbor points for data. This graph distances are arranged in the ascending order to plot a curve, which you can see in the figure. As it's provided, the dataset had multiple variety of densities. Each elbow on the curve specified one optimal value for epsilon. The epsilon's optimal value corresponding and considering not eliminating the valuable points exists in the first elbow, which is 0.00002. It's presented in as a dashed line on this figure. The dbScan algorithm successfully clustered the dataset's state points regions. dbScan clustering was performed in WCA version 3.6.9 on 7,831 GPS data for 8 seconds with a minimum point of 3 and epsilon of 0.00002. The result generated 133 clusters and 5,334 for non-cluster data. In total, we achieve 5,467 new points for the map matching process. This figure states the detailed performance of dbScan clustering for alternative elbow on the curve. Clarified other noteworthy values of epsilon for more comparison. After identifying the state point cluster in the dataset, each point is replaced by 1 point, and the surplus points are removed from the dataset. The replacing data elements attributing equalized the average features of state point on the cluster. The effective efficiency and adequacy of our approach on two parts of the real trajectory dataset is shown in this figure. The fuzzy logic-based map matching algorithm is implemented on the raw data and also the state point eliminated dataset to obtain the experimental result. The previous approach were implemented by the RStudio version 3.4 and run on a computer with an Intel Core i5 processor and 16 gigabyte memory in macOS. Subsequently, both procedures are compared based on four metrics: accuracy, processing time, speed, and volume efficiency. Both approaches identify the same road path and the ground truth data with the same number of correct link identification. Our method maintain the previous approaches accuracy with more proficiency. This figure illustrated this subject matter in more detail. For time efficiency, the processing time of the map matching algorithm declined by 8.9%. The result of this evaluation among two approaches clarified in this figure. The dataset volume decreased by 27.39%, significantly impacting time and storage resources. This matter is pointed out in this figure. Our approach performed a faster execution time by 21.42% than the earlier method. This figure referred to more elements of this subject. So, to conclude this research, we discussed the challenges faced by map matching method in balancing accuracy and processing time. We focus on state points as a factor contributing to increase processing duration. The research included the use of DB scan algorithm to identify state point regions in GPS trajectory and move redundant data, resulting in improved efficiency of a fuzzy logic-based map matching algorithm. The method is evaluated against ground truth data, resulting in an 8.9% reduction in processing time, a faster performance pace for each point, and a 21.42% increase in execution speed. The processing method can be utilized as an offline pre-processing step for analyzing moving object datasets. In future works, we aim to explore diverse datasets containing unconventional state points and other unusual trajectory points to analyze vehicles' immobile behavior and enhance urban planning management. We also highlight two critical challenges faced by map matching algorithms. Firstly, the inadequacy of subsequent trajectory in critical regions, particularly border points, which is prominent in low-frequency sampling data. And secondly, the presence of Y-shaped junctions. These issues lead to inaccuracies in link identification. The intention is to find the optimal solution to address these challenges in future research. The reference points are available for further exploration. Thank you for your time, and this is our reference points.